Today we're going to look at limit laws, which will allow us to do some of the limit problems from last time much easier. They really simplify quite a bit, but you just have to be careful about how you use them because you can still step into some mud if you're not careful. So here are the laws themselves, and it looks pretty complicated. Basically, well, these are the first few laws. But basically, it's just common sense for some of these. Like, for example, if you have the limit of two functions added together, you just add the limits together. In other words, if you want, you can think of the limit property as being distributed through. Okay, same thing with subtraction, it's just distributed through. So like this. So limit of f of x minus g is limit of f of x minus limit of g of x. That's right here. So one way you'll see this is limit of, let's say, limit as x goes to 2 of x squared minus x. You can make this, you can distribute the limit through like this, and it'll be limit as x goes to 2 of x squared minus the limit as x goes to 2 of x. And then there's going to be a rule later on where we can just plug the 2 in. I'll show you in a minute. You can plug the 2 in to these two directly and just get the answer. So you get 2 squared minus 2, which is 4 minus 2, which is 2. Okay, so that would be the limit of this. Now, you could look at this and say, well, why can't I just plug in 2 right now and just get a limit as x goes to 2 of 4 minus 2. And so you would get limit as x goes to 2 of 2. And now the limit of a constant is just a constant, so it's that right there. The reason it's a constant is because a constant is just doing its own thing. It doesn't care what x is doing. Okay, so another way you can see this is graphically, and I'll get to that in a minute. All right. Okay, so that's that. And now, if you take the limit of a constant times a function, you can pull the constant out, like right here, it's pulled out. The limit of a product is the product of the limits. Okay, so like for example, I'll do one of those. Just get rid of some of this. You could do, for example, limit as x goes to, let's say, pi. Let's make it pi over 2 of x times sine of x. And so this is the limit of a product. You got to be careful though, because one of these limits doesn't exist. You can't do this. So limit as x goes to pi over 2 times x times the limit as x goes to pi over 2 of sine of x. And now you can just plug them in. The limits have to exist in order for you to do this. So you just plug that in, plug this in, sine of pi over 2. And so this is pi over 2 times 1, which is just pi over 2, because this ends up being just 1. The limits have to exist for you to be able to do this. Okay, and it says it right here. Okay, it says these two exist. Okay, if they don't exist, if one of the limits doesn't exist, you can't do this. All right, so we're assuming that this stuff exists, that these limits exist in order to use these rules. So you have to be careful. For example, I could have just as easily picked, let's use a different color, limit as x goes to pi over 2 of x times tangent x. But the tangent of pi over 2 is positive infinity. Okay. Well, I guess you would get pi over 2 times infinity, which is infinity. But sometimes we say if the limit is infinity, it doesn't exist. This is actually okay. If I think of a better example, I think later I'll bring it up. The limit of quotient is the quotient of the limits, so you can distribute it and know it's the top and bottom. This is a big one here. The limit of a function to the n power, you can distribute the limit through and then take the n power into consideration. So that's kind of what we did before. Let me rewrite it over here. What we did was, so here's this limit as x goes to a of f of x to the n power is equal to the limit as x goes to a of the function, and then you raise it to the n power. An example of this would be the limit as x goes to, let's say, 1 of, let's say, x to the 3 power, not 1. Let me make that a 4. So you could plug the 4 in. So this is the limit as x goes to 4 of 4 and raise that to the 3 power. And now that's just 4 on the inside, which is just 64. Yeah, so there you have it. This one here comes in more often in more complicated problems, and we'll see those pretty soon. Okay, so the limit of a constant is a constant. Let me show you why that's true. And then the limit of x as x goes to a is a. I'm kind of already using this in some of these problems, but let me show you why this one's true. Limit of a constant is a constant. So why? Well, the limit of a constant as x is going to a, this is a function. Okay, so this is y equals c. All right, just like let's see over here. This is a function, right? Y equals x sine x. And what the limit is going to give you is going to be the y value of the function as x is, in this case, as x is going to pi over 2. So whatever this looks like, the limit as x goes to pi over 2 will have a value. The y value there will be pi over 2. Okay? So when you graph this function at pi over 2, what do we get? Pi over 2? Yeah. Yeah. At pi over 2, the value of the function is also pi over 2. All right? So the limit, remember, is the y value. So here, what we have is the limit of c as x goes to a, and we're trying to see what this is. So y equals c is the function. Okay? So y equals c is a constant. So let's suppose the constant's positive. So c is greater than 0. So what you'll have is, let's graph this in purple. Here's y equals c. Y is a constant. Y equals a number is a horizontal line. Okay, so we have the x-axis, we have the y-axis. Now, as x goes to a, let's suppose that a is, I don't know, suppose it's here. As x is marching toward a, on either side, the value of the function is always going to be a. The value of the function is always going to be c. I'm sorry, it's going to be c. Because this number right here is c. Okay? So no matter how far out from a you go, the value of the function is always going to be c. So this one's actually pretty simple, unless you're not getting the concept. The limit, this limit, is just going to be c itself. Okay? So a little mini example of this would be limit as x goes to 2 of 17 is just 17. Okay. Another way you can look at it is there's no x to plug into. All right. So if there's no x to plug into, then this is pretty much just the answer there. Okay. Okay. So let's move on. The limit of as x goes to a of x is a. Here's another example where this is just a function. All right. So let's pull this over. Let's pull it over here. So it says the limit as x goes to a of x is a. So it looks like you can just plug it in. Let's see y though. This is y equals x. This is always your function. When you graph this, when you graph y equal x, that's just y equals x is this line right here. It's the 45-degree line. If you don't know that, you need to know that for this class. Okay. So let's suppose that a is on this side this time. So here's a. Now as x is marching toward a, the value of the y value there is going to be right here. Well, if this is y equal x, and x is marching toward a, then this must be a also, because this is the line y equal x. So whatever x is, this is the x-axis, whatever x is, y is. All right? So you can just plug this in, and you just get a. And that's why the limit as x goes to a of x is just a. All right. So I think this one's pretty self-evident. It says the limit as x goes to a of x to the n is a to the n. I'll let you study this one. If it's a root, you can just plug in the value. And then this one is if you take the nth root of a function, it's equal to the nth root of the limit of the function. We're assuming that the function's positive. What's a good example of this? You can look at limit as x goes to 2 of the cube root of x squared plus 4. All right. So what I'm going to do is I'm going to plug in the 2. So this is equal to the cube root of the limit as x goes to 2 of x squared plus 4, which is going to be the cube root of, now you can plug the 2 in, and now you get 4 plus 4, which is 8, cube root of 8, and you get 2. Now we got the answer 2. It's just a coincidence. It had nothing to do with this 2 here, okay? All right, so essentially what it says is you can take this limit and you can plug it in here. It distributes into the root. Once again, you have to be careful. If the limit is negative, you can't do this. It's got to be positive. All right. So here's a great thing. The direct substitution property. It says if f is a polynomial or a rational function, and a is in the domain of f. So in other words, if you plug a into f, it makes sense. It gives you a number back. Then you can just plug in a. So polynomials, you know what polynomials. A rational function is a ratio of two polynomials. So an example of a rational function is f of x equals x squared minus 2 over x plus 7. Okay, so it's a rational function. It's a ratio of two polynomials. So there you have it. So if that's the case, if you have a polynomial or a rational function, your limit can just be plugged in. Okay, so for example, if you have limit as x goes to let's say 3 of x squared minus 6 over x plus 4, you can just plug the 3 into, this just becomes limit as x goes to 3 of x squared minus 6 over limit as x goes to 3 of x plus 4. Okay, so you just get your answer. Just plug it into both. So this is just 9 minus 6 over, this is a 4. 3 plus 4, which is 3 over 7. And there you go. All right, so with that said, we can move on to some other things. This I'm going to leave for you to do these yourself. This is just applying the same topics, same ideas with a graph. So I'll let you play around with that. If there's any questions, just ask in the Q&A. All right. So these can get kind of difficult here. So let me do a few of them, or a couple. It's really just a bunch of algebra going on. Let me do 14. So 14 says limit as x goes to 4 of x squared plus 3x over x squared minus x minus 12. Now, if you just plug 4 in directly, you get 16 plus 12 over 16 minus 4 minus 12. So, is that a plus on the top? Yeah, it's a plus on the top. Okay, cool. All right, so what you're going to get here is 28 over 0, which is bad. All right. You don't like this. So, no, we don't like this. No. And that's exactly what you get, but you get 0 in the bottom, which you don't like, which is not good. So you can't do anything with this. It could be infinity, but let's check it out. I'll tell you what. Actually, yeah, let's factor this and see what happens. Okay. So instead of doing this, let's factor it and see what happens. So this is equal to the limit, and I want you to write limit. I'll tell you what, let me erase all this. I want you to write limit every time until you actually apply the limit, okay? So this would be x, take out an x plus 3, and then this factors into x minus 4 times x plus 3. The x plus 3's cancel, and you end up getting limit, so this is equal to limit as x goes to 4 of x over x minus 4. You're still going to get 0. Yeah, so this is one that's a little tricky. If you plug in 4 and plug in 4 there, you're still going to get 4 over 0, which is infinity. Okay, so yeah, my intuition was right. It turned out to be just infinity after all. But sometimes if you get like 0 over 0, you run into trouble. Okay, I would recommend you always factor though, because a lot of times things will cancel, and it'll be better for you. Number 20 is probably a good example of it. 20 says, I'm going to use x, limit as x goes to 1 of x to the 4th minus 1 over x to the 3rd minus 1. I think that's it. Yeah. All right, so I'm not going to walk through the factoring necessarily as far as like where I'm getting these numbers. I just want you to look it up online. The top one is the difference of two squares. It's x squared minus 1, x squared plus 1. If you have any questions about what I'm doing in any of these videos, just ask in the Q&As, or you can email me. Plenty of students have already done that. So this is x squared plus x plus 1. There's a formula that I'm using here. Okay. When you use that formula, the second parentheses is not factorable. Okay. All right, so you can't ever factor that. Okay, so moving on, we move to the right some more. Let me get rid of these guys. We got limit as x goes to 1. The top one factors into x minus 1, x plus 1, and then the x squared plus 1 doesn't factor. And we get x minus 1, x squared plus x plus 1. The way this factors into like this, there's a word they use, SOAP. Same, opposite, always positive. Maybe that will jog your memory on how to factor the difference of two cubes. All right, so we factored it again. It looks like the x minus 1s, those cancel. And this doesn't factor, of course. This doesn't factor. It's a sum of two squares. So now, if you had plugged in 1 immediately, if you had plugged in 1, notice that it would have given you 0 times everything over 0 times everything, which would have been 0 over 0, which you don't know what to do with. We're going to have to wait for Cal 2 to deal with that. But here, you can cancel these x minus 1s instead. and then you don't get that problem. So when you plug in the 1 now into what's left over, which is all of this, you'll get 2 times 2 over, let's see, what's that? Plug in 1, you get 3, which is 4/3. And there you go, there's your answer. Okay, so factor first, all right? There's some tricky ones, like 18 is a good one. I'll let you deal with that on your own. 30, you'll have to rationalize looks like you might have to rationalize the numerator there. Look in the book for an example of that. If you don't see it, just ask me. I want to do, which one's a good one? I want to do this one here, because this is going to come up later in a different guise. So, looks kind of bizarre, but it's actually very useful. So let me rewrite it. Let's see here. It's limit as h goes to 0 of 1 over x plus h quantity squared minus 1 over x squared over h. So let's see. Let me erase some of this too. All right. Okay, so this here requires some intermediate algebra. So this is math 0 through 10 here, intermediate algebra. What you can do is you can multiply the top and bottom. Well, you can cross multiply to get the numerator into a form where you can actually plug in h. Now notice if you plug in h right now, there's danger in that because you'll get 0 on the bottom. You'll get something over 0, which is bad. Okay, so what you want to do is you want to manipulate this until you can plug in 0 for h. Okay, so what I'll do is I'll try to make this one single fraction. Okay, one single fraction. There's a bunch of fractions. I want to make it a single fraction. That's my goal. Okay, this is the goal. All right, so I'm going to go ahead and analyze the top, or manipulate the top. This is x squared minus x plus h quantity squared over x squared times x plus h quantity squared all over h. So to go from this numerator to this numerator here, okay, I just use this little fact. I encourage you to analyze this. A plus b, a over b plus or minus c over d is equal to AD plus or minus BC all over BD. Okay, so I just cross multiplied, and then I multiplied the bottoms. All right, so just test that if you want. Now I'm going to keep writing. I'm going to keep my limit going. Limit as h goes to 0. Now I'm going to use, this time I'm going to use a little fact. If you have a over b over c, this is a over bc. Okay, so here's a, here's b, and here's c. So I can go ahead and combine this denominator here and this denominator here, and I'll get, so let me write down the numerator. The numerator is x squared minus x plus h quantity squared over h x squared times x plus h quantity squared. All right, and now I still can't plug in 0, okay? No way, Jose. So, because I'll get 0 times a bunch of stuff, which will equal 0. So I have to play around with the numerator. Let me play around with the numerator. So it's limit as h goes to 0 of x squared minus 2xh minus h squared all over. And now the bottom, I'm just going to keep like it is. There's no point multiplying this out. By the way, canceling here and here is bad. Don't do that. Please don't do that, okay? It's a major mistake. There's a minus sitting there which prevents you from canceling this top term with this bottom term, okay? So please don't do that. I'm not saying you would have, but plenty of people do, okay? So just be careful. If you do that, everything else is wrong afterward. All right, so I'm going to go ahead and keep the the x squared out, and then x plus h quantity squared. There's no point multiplying that out. But if you look at the top, x squared minus x squared is 0, and then you can cancel out. You can, let me go down, limit as h goes to 0. You can take out an h, and you get negative 2x minus h, and then on the bottom, x squared times x plus h quantity squared. What I did was I just factored out an h out of this, okay? Now, if you look, these two h's cancel, and you can plug in h equals 0 now. So finally, you can plug it in. And when you do that, you get, okay, so we have h is going to 0, but this cancels, these cancel, and so I get negative 2x minus 0 over x squared times x plus 0 quantity squared. And when you figure this out, you get negative 2x times x cubed. One of the x's cancels, and you get negative 2 over x squared, and that's the answer. So it checks out. Okay, so there's that. All right, so there's some other problems that, kind of get difficult as well. The one thing I wanted to point out, though, is that what we're doing here is the derivative, which is going to come up later, and that is the derivative of this function, okay? So you're going to need to know how to do problems similar to this, just maybe not quite as hard. The other thing I want to point out is it's really helpful if you know this formula, and it's really helpful if you know this one, okay? All right. Don't memorize them, just learn how to use them, and then you don't need to memorize. Okay, what's the next one here? If f and yeah, here we go. If f and g agree everywhere except a, maybe, then their limits are the same. You could possibly see something like, all right, I erased everything. You could possibly see something like this. You'll see this probably in the homework. You'll have a function f, there's f of x, and you'll have a function g of x, which is the same thing, except g of x, okay, so here's g of x in blue, except there's a dot in the middle, let's say, oops, there's a dot in the middle here where g of x is up here, okay, and at that dot, that point is a, that x value is a. So g of a, suppose this is b, and that the limit here is L. So g of a is b, but everywhere else, okay, so everywhere else, g of x is f of x. Okay, well, the limit doesn't really care what's going on at a so much as around a, okay, as around a. So the limit of g of x as x goes to a is still L, which is the same thing as the limit as x goes to a of f of x, okay? They're both, as you get to a, as you get to closer and closer to a from each side, that limit is still right here, okay? It's going to be this point right there. Okay, so moving on. Actually, this is a good example one, and this is in the book, okay? So read the book on that. What's coming up? This says that the limit basically is a if the left and right limits correspond. The limit as x goes to a is L if the left and right limits correspond. We talked about that last time, so watch the video from last time. This is important. Show that the limit as x goes to 0, the absolute value of x is 0. I want to show you this one because it comes up quite a bit, and you really have to know how to work with it. In fact, I need a lot of room for this one, so let's move it over. Let's go up here. So let's show that the limit as x goes to a, x goes to 0 of absolute value of x is 0. There's two ways to do this. The first way is just to graph it. Just look at the graph. If you know what the absolute value looks like, which you should from college algebra, and I really want you to know what it looks like. It's this guy right here. It's the two 45-degree lines, 0. All right, so this is the absolute value of x in red. And as x marches toward 0, you get 0, okay? So is this what we were trying to find? I'm trying to think. This is a little too easy for what? Yeah, 0. Okay. So another way to look at this, and this seems like it's going to be a little more complicated, so why isn't the graph good enough? Well, because it'd be helpful if I just told you that you need to understand that the absolute value has an algebraic definition as well, okay? And this is it. So I need you to memorize this, okay? Please memorize this. It's not hard if you just think of the graph, okay? So look at graph. So basically it says if x is less than 0, if x is less than 0 inside here, like if it's -3, then you multiply that number inside, by a negative, and that'll make it +3. So this is why the absolute value of -3 is +3, okay? That everybody always tells you it's the distance from the origin. That's that too, but you can look at it in an algebraic sense as well, okay? So in this expression, in this definition, so this is a definition of absolute value here, when x is equal to 0, the answer is just x. So if you have the limit as x goes to 0 of the absolute value of x, well, as x is going to 0, you're just going to get 0. Now, that's the case if you're coming in from the right. See, we're coming in from the right, where x is greater than 0. X is greater than 0 over here. What about if you're coming in from the left? Well, as you're coming in from the left, if you plug in values closer and closer to 0 from the left, like -0.0001, -0.00001, things like that, you're going to eventually get 0. And so that's why the answer is 0. Why? Because the left and the right hand limits correspond. So we're using Reason's theorem to prove example 7, which is in the book. So here is the deal with that definition. See all these absolute value functions in here? You're going to want to understand how to deal with them, okay? So the hard part is knowing how to use the algebraic definition here very carefully. So let me start with one that's just a little easier. Let me start with 42. 2x plus 12, x plus 6. So it says find the limit, it's 42, find the limit as x goes to -6 of 2x plus 12 over, is it x plus 6? Yeah, over x plus 6 in absolute value. Okay, here's the thing. Let's get a handle on what x plus 6 is, okay? So x plus 6, we're going to use that definition we had before. It's just the interior if x plus 6 is greater than or equal to 0, and you put a negative on it if x plus 6 is less than 0. So either rewind the video or let's look at it. Where was it? It's up here. It said, I'm just using this definition here for absolute value, okay? So what you do is you take the interior, let's just look at this in green. You take whatever's inside, put it here, and you put it here with a negative on it, and you put it here and here with a greater than or equal to and a less than 0, okay? And so that's what we did with the x plus 6. So let me just write that here so you'll see the similarity. So before we had x plus 6, and then we go equals, and then I'm going to rewrite it up here, x plus 6, and then x plus 6 is greater than or equal to 0. Get rid of this limit. All right, and then I'm going to rewrite it there. So x plus 6, and then x plus 6 is less than 0 here. Okay, so with that said, okay, so I'm going to go back down to the problem. We can go ahead and solve the right-hand side of these. This is x plus 6. This is negative x minus 6. Over here, this is where I'm going to solve this, and I'm going to solve this. X is greater than or equal to negative 6, and then x is less than negative 6. Okay? So, with that said, we have absolute value of x plus 6 written out very precisely, okay? Written out very precisely. And now I can use that to deal with this limit here. So basically what we're doing is we're coming in to negative 6 from, does it say left or right? No, just from the negatives. Coming into negative 6. Okay. So if we're coming into negative 6, let's see what this is here. Okay. What we can do is we can factor this. So we go limit as x goes to negative 6. And now this whole function becomes 2 times x plus 6 over x plus 6. I'm using this. The absolute value I can rewrite with all this down here. And then this is when x is greater than negative 6. Look at the bottom there. That's where I'm getting it from. And then it's 2 times x plus 6 over negative, and then x plus 6. You don't have to distribute the negative. You could have left it out. It's like in here. So you can just rewrite it like that. These cancel. These cancel. And this right here was x is less than negative 6. So what you get out of this, wait, how did this problem is not simple, is limit as x goes to negative 6 of 2 or negative 2. X is greater than or equal to negative 6, and then x is less than negative 6. Now the limit does not exist because as you go to negative 6 from the right over here, you get 2, and as you come in from the left, you get negative 2. So let's just graph this. So what this function looks like is the following. Here's negative 6. Okay, so the graph, get rid of this piece, is 2 when x is greater than or equal to negative 6. So it's 2. This is y equals 2, and then this one here, this is y equals negative 2. Y equals positive 2 is a horizontal line at 2. Okay, oops, it's only this here. And then y equals negative 2 is a horizontal line, but this one's open. This is y equals negative 2, x less than negative 6. Okay, and then this red one here is y equals 2, x greater than or equal to negative 6. I'm getting that from these two up top. Okay, all right, now as x is going to negative 6, so x is going to negative 6 from either way, you get different values. okay, you get this value, and then you get this value, okay, right? So coming in from the left, you get -2, and coming in from the right, you get +2. And so the limit does not exist. All right, so play around with the absolute value problems. If you have any questions, ask me in the question and answer. I like this problem here, but I like this one better, and I like this one better, and I like this one better. This is more like what you see later. Okay, what else we got here? Squeeze theorem, and that's it? Yeah, okay, cool. This is an important theorem. I'll let you look at this on your own, so you study. This is all in the book, by the way. This is called the squeeze theorem. And what this says is if f and h, if the limit of f and h is L, and g, as x is going to a, as x is going to a, and g is between them, okay, when x is near a, then the limit of g has to be L also, okay? So it's easier if you see a graph of this, actually. So let me graph this. So what it says is this is the squeeze theorem. Okay, so it says this basically. You have three functions. You have h, and then you have f. Oops. Yeah, f. And you have a g. Let me do g in green. So g is here. G is moving along. And this is g. Okay. So at A, they all, f and h correspond, and we're going to call that value L. Okay. So this is A. So the limit as x goes to A of f of x, as x is marching to A, the value of f is L. The value of f is L. That's the y value. And then, so that's L. And then the limit, sorry, L. Also, the limit as x goes to A of h of x is also L. Same thing happens with the blue graph, right? It's also L. Okay, so if this is the case, then this implies then that the limit as x goes to A of g of x also has to be L, since f of x is, f of x is less than or equal to g of x, and g of x is less than or equal to h of x near A. Doesn't even really matter what's going on much further out than A. But near A, so near A, in a little region around A, those inequalities are true. And if that's true, then if h is going to L over there and f is going to L over there, then g has to go to L also. Now, you're probably thinking, well, maybe you're not thinking this, but a question might be, where would you ever use this? Well, if you don't know what the function is, okay, but you know that the outside functions are going to the same number, then you know that the inside function is as well, okay? Okay, but the meat of this problem is more like in this here, okay? So I want to do number 40. That's sine of pi over x, square root of x. Okay, so let's do it down here. So it says limit as x goes to 0 from the right, this is 40. You'll see one of these on a test. All right, of the square root of x e to the sine of pi over x. Okay, show this is 0. So is this 0? So it doesn't say is it 0, it says show it 0. Show it 0. Okay. So what do you do with this? Well, who knows? Gosh, this looks horrible. But let's see. Well, I do know that so we got, let's see, we got sine of pi over x. I know that's less than or equal to 1, and it's greater than or equal to -1. This is because sine is always between -1 and 1, right? Sine of theta is always between -1 and 1. Now, if I had multiplied sine by a number or manipulated it any other way on the outside of sine, this would not be the case because this is pi over x. Pi over x, though, is still, it's just theta. Now, if I had put a 2 here, now this is, now I can't do this. I can't do all this, okay? But there's not a 2 there. I didn't put one there, okay? Okay, so I know that sine is between -1 and 1, all right? So this piece up top here is what I'm starting with, okay? Now, e to the x, so it's e to the sine, right? E is an increasing function. I need you to know what e to the x looks like. So this is e to the x. It increases, okay? Please memorize this graph, okay? If you don't remember what it looks like, go to an old algebra book. It's an increasing function. So if I take e to that power, that's also increasing because, well, wait a minute. I don't need this -1. I know that it's also greater than 0. Yeah. It's greater than 0. That's what I want. Okay. So now e to that power is also going to be, let's see, it's also going to be greater or equal to 0 because e never hits 0. It never hits 0. It never hits the x-axis, okay? So then, let me draw this smaller. Now, on the other side, I have e, going to raise that to the 1 power. So I raise all of these to the 1 power. Now, e to the 0 is going to go over on this side, and that's equal to 1. So what I'm doing is I'm taking all 3 sides and I'm raising e to all 3 sides. And since e is an increasing function, then the inequalities stand. This wasn't the case when it was -1. That's why I made it 0. It's still the case that sine is between 0 and 1, okay? All right, it's still a true statement. Okay, now e to the 1 is 1. E to the 0 is 1. So this is 1 less than or equal to e to the sine of pi over x is less than or equal to e, okay? E to the 1 is e. All right, so now I still have the square root of x to deal with right here, okay? So I'm going to multiply everything by square root of x. Square root of x is an increasing function too. So if I multiply all 3 sides by square root of x, the inequalities still apply. Okay, so we'll multiply that by square root of x. Square root of x times 1 is square root of x. Square root of x, e to the sine of pi over x. And then less than or equal to e times the square root of x. If it were not an increasing function, okay, if it were something like 1 over x, then this is not the case. The inequality signs may switch around or something, okay? You don't know. But since it's an increasing function, you can still do this. So now, the limit is as x is going to 0, okay? So now let's do the limit on both sides. So as x is going to 0, the square root of x is going to 0. As e square root of x, as x is going to 0, e square root of x is also going to 0 because the square root of x will be going to 0. And since the outside functions are going to 0, we know that this one is going to 0 as x is going to 0. And there's an example of how the squeeze theorem is used. Okay, now there's some cool applications at the very end here. And if we get time, I'll go over these. This one's kind of cool. It takes a little while. This one's really cool. So if you can look at this, that would be great. So look at this. And if you have any questions, just ask during the Q&As. Okay? So that's those are the limit